Okay, so we're going to go over solving consistent equations for three planes. And the reason they're called consistent is that in all situations, you will have what is essentially one answer. Okay, so in case number one, all three planes will converge at a single point. So some coordinate in space. Okay. In case number two, all three planes will converge at a specific line in space. So some vector will represent their point of intersection. Equation 2b, you could call it case 3, or sorry, case 2b. What you have is two planes that are coincident planes, and they will converge with the third plane on some vector in space. So again, it's still consistent. There's still one answer. And finally, you have three planes that are coincident planes. So they all have an infinite amount of answers. Okay. What we can do is we can always check for case 3 and 2b right off the start, depending on what our question is. We'll use inspection to look to see if we have any coincident planes. And then if we don't, then we can get into looking to see if they're a consistent system of having one vector representing their point of intersection or a specific coordinate. Okay, so we're going to take a question right out of the book here. I forgot to prepare for it, so give me a second. So we have three planes here. Okay. First plane represented by this equation, second plane, and the third plane. Like we said, the first thing we want to do is check to see if we have any systems or planes that are identical or scalar multiples of each other. Okay, so we'll quickly stack them on top of each other. It'll probably be easiest to look at it that way. Equation 1 will read x minus y plus z is equal to negative 2. Equation 2 is 2x minus y minus 2z equals negative 9. And equation 3 is 3x plus y minus z is equal to negative 2. If we quickly look, the first one I should be able to multiply by 2 according to my x values. Not the case, so not a scalar multiple. I should be able to multiply by 3 to get to this one. Not the case with the y's again. And between these two, according to my z's, I should be able to multiply by 2. Not the case with my x's. So none of these are coincident planes. Okay? So all of these are three different planes, which means we either have three planes intersecting at a line or at some coordinate in space. We're going to go about doing this the same way I had done before. We're going to pair up equations and eliminate one of the variables. So I'm going to work with eliminating x to start. I'll take equation 1 and 2 and then equation 1 and 3. Equation 1, I'm going to multiply by negative 2. So we'll have negative 2x plus 2y minus 2z is equal to 4. And equation 2 is 2x minus y minus 2z is equal to negative 9. Okay. Scroll down a little. We'll equate what we get here. These two will cancel out when we add them. When we add these together, we'll get y. And when we add these together, oh, they will also cancel out. Okay. So we're ending up with y is equal to negative 5. That actually became very helpful. We've jumped to a third step. We still need to make, and we'll call this equation 4, we still need to make an equation 5. So I'm going to use equation 1 again, but this time I'm going to multiply it by negative 3. And the reason being is because equation 3 has a coefficient on x of positive 3. Yeah. Oh, you're right. Good. Good, we caught that mistake way before this. This should be negative 4z is equal to negative 5. That's fine. Our equation 4 is actually a line, or an equation here, so that we can deal with this the way we originally planned. And we'll take equation 3, or sorry, equation 1 multiplied by negative 3. We get negative, yeah. This one I multiplied by -2. Yeah. So let's go back to this one here. -3, we're multiplying it by -3, so this becomes positive 3y, negative 3z, and -3 times -2 is our 6. So same idea. We're going to add again. These will cancel out. This becomes 4y, this becomes -4z, and this becomes the value of 4. So we have equation 4 and 5. We're going to take equations 4 and 5, and we're going to subtract them to eliminate a variable. I'm going to eliminate y, which means I want to take equation 4 and multiply it by -4. So equation 4 multiplied by -4 gives us -4y plus 16z is equal to 20. And equation 5 is 4y minus 4z is equal to 4. We're going to add these again. Our y's will cancel out. Here we'll get 12z, and here we'll get 24. So in this case, z is equal to the value of 2. Now that we've done that, we've got an actual coordinate. So because we have a coordinate, we're going to get a coordinate in space. Okay? We didn't run into a situation where we're dividing z as 0 and 0, which would give us an infinite amount of answers, which means we'd have a line. So we know we have a coordinate. We're going to go about plugging the z into either 4 or 5. We'll take equation 5. 4y minus 4 times 2 equals 4, which gives us 4y equals 4 plus 8. Y is equal to 3. Yeah. So we have a z2, y3, and we're going to plug into one of the original equations, x minus y plus z. That's our equation 1. X minus y plus z equals, I think, -2. Yep. Yeah. So we have a value for y and a value for z. So y is 3, z is 2. We'll plug it in to solve for x. X minus 3 plus 2 equals -2, which means we have an x value of -1. Okay. So our coordinate in space here, these three planes connect at a specific coordinate, not at a line.